Hi NA Physics, it's Mr. Neff. Today let's talk about RC circuits. When I say an RC circuit, I mean exactly that. I mean a circuit that has a resistor and a capacitor in it. Now, this is a thing that is going to take some time to come to a steady state, or a place where the capacitor is quote-unquote full for that amount of EMF or voltage. We're going to have two real simple circuits in class here, and then we'll move on to something a little bit more complicated. We're going to have one where you have a battery, a resistor, and a capacitor, and the capacitor is going to start off uncharged, and we're going to charge it up. And then we're going to have the opposite, where we're going to remove the battery, and then we're going to have just the capacitor and the resistor, and we're going to discharge it. Here's a nice simulator from our friends over at FET, and you can see that we have a one D cell, and it has a maximum voltage of 1.5, which I just turned it up to. I put a voltmeter across an uncharged capacitor. Now, as you can see, when I click this circle, that's going to close the switch top and bottom, and current is going to flow. There's not any appreciable resistance in this circuit, and so you're going to see that things are going to happen really fast. Click, done. The circuit has charged, the capacitor has charged fully. The voltage across the capacitor is the same as the voltage on the battery, 1.5 volts, and it happened just like that. Now, I'm not going to say that that happened instantaneously, because that's not quite true, but because the resistance of the wires is really small, that means that the time that it took for that to charge and become into a steady state is really, really small. Now what I'm going to do is I'm going to allow that to discharge through the resistance of that light bulb. And if I do that, you're going to see things are going to change, but it's not going to happen instantaneously anymore. I'm just going to move this up for us just a touch. I'm going to show you the top plate charge. I'm going to show you the stored energy, and ready, here we go. And you see how that went from a 1.5 volt potential across there down, and it still isn't there yet. It still isn't there yet. Finally, after quite a bit of time, way more time, we had the voltage of the capacitor go all the way down to 0. So we're talking about the same amount of energy in the first instance and the second instance. Here again, first instance, I got an amount of energy stored on that capacitor, an amount of charge stored on there, just bam, lickety split. But then whenever I discharge it through resistance, that resistor is going to impede the flow. And so the same thing's going to happen, but it just happens way more slowly than it would have happened otherwise. Now here's another nice simulator from our friends over at Geogebra, and they have taken it up a notch because they are allowing us to see a charging and discharging circuit in the same circuit. It's just similar to what I just showed you, but a schematic view. And at the same time, it'll give us a graph as a function of time of the charge or the voltage or the current, which are the three quantities that we're going to be interested in here. So let's go with charge first. So now what I'm going to do is, you can see here we have a shorting wire across the center, which when that switch is closed, that's going to cut out the EMF over here on the left, and it's just going to be capacitor resistor. I'm going to leave that open for now. I'm going to have this top switch closed, and so really I have the charging circuit. I have a EMF over here. Conventional current's going to come up, going to come to the right, hit this plate. That's going to push conventional current from the right plate down through the resistor and back. Now that resistor is something that I can control here. Let me get a little bit out of your way. There, the resistance, and I can control all of those things. I can control the resistance, I can control the capacitance, and I can control the voltage. Now, what I'm going to do is I'm going to get this started, and I want you to think, what is this graph of charge as a function of time going to look like? By the way, you can see that they already have a dotted line placed in here. This was a great idea. They have the charge maximum as 240 microcoulombs. Can you see where they got that from? Well, yeah, of course. They took that capacitance and they took that voltage and they multiplied it. But you can see that we're not going to be there right away. It's going to take some time to get up to that. It's going to take some time to get up to that steady state. So if I click play, now you're going to see that at first things start to happen really quickly. And if you were noticing on the simulator, things happened pretty quickly there too. I'm going to pause it there for just a second. Now, you might not have thought of this right away because it's not the most intuitive thing in the world, but they say that R times C is 1 second. And that is true. If you take that resistance of 100 kilo ohms and the capacitance of 10 microfarads, go ahead and do it for yourself if you need to, you will see that actually comes out to 1. And if you play with the units on that, you end up seeing, and yet who would ever think, right, that the resistance unit times the capacitance unit, SI units, will give you the second. Well, it's true, but that's not something that you would have seen coming. So that R times C value is an important value, and we call that the time constant. A lot of times that's abbreviated as a symbol tau, Greek letter tau. And that time constant is basically in control of how quickly the thing is going to get up to its steady state or come down to zero from its steady state. So you can see here that in one time constant, right here, you shot up to, about this far. Now, knowing what I'm going to teach in a second, I know that that's about 68%. And then in 2 time constants from the beginning, you shot up to this value. Well, how much is that compared to how far you'll eventually get? Well, again, knowing what I'm going to cover in a second, that's about 86%. And it keeps on going from there. Now, if I let this run even farther, it's in about 5 time constants, we usually say that it's pretty darn close to steady state. It's not going to be exactly steady state, so that there's your 6th time constant, 7th time constant, and so forth. Now I've reset that, and now what I want to do is I want to change the time constant. So I could change that either by adjusting the resistance or adjusting the capacitance. You can see that in this particular case, the R times C product was as big as it could be because both the R and the C are as big as they can be. So I'm going to take this R and I'm just going to move it down. I won't mess with the capacitance, although I could have. Now I want you to think, what happens now? What happens when I click play in terms of this graph of charge versus time? Well, maybe you were right. In terms of the time constant, the same thing is happening, but the time constant in real seconds is less. So the whole thing is happening a lot quicker. I've reset this one more time, and just 2 more things before we leave this. If I showed you a graph of voltage versus time, how would that look? Well, it turns out it's going to be exactly the same shape. You know, values are different because now we have volts on the axis instead of coulombs, but it's going to be exactly the same shape. And if I were to refresh this one more time, and now I want to show you a graph of current as a function of time, you can see what's going to happen here. And now the current is not going to be the same shape. The current's going to start off really high. In fact, the current is going to start off just as the voltage divided by the resistance, because at first the capacitor is uncharged and it's not resisting the flow at all. And then as you get more and more charge built up on the positive plate, it gets more and more difficult. And so the current comes way down. And so you can see that was just happening there. So it would be really nice if we could predict all of those things. And we actually can very, very easily. So on a charging circuit, like what we saw in the first place, we can say that the charge as a function of time is going to be the maximum charge, which again we said is the capacitance times the voltage. So if I can pencil that in right there, this is also going to be the capacitance times the maximum voltage, and times a thing that's going to give you that curved shape but asymptotic to that maximum charge. And so that's going to be a function that involves the natural base, the e. And so we have 1 minus e to the negative t. This is the amount of seconds that you're talking about. If you want to know how much charge is there after 2 seconds, you'd put a 2 there. If you want to know how much charge is there after 10 seconds, you'd put a 10 there. In the exponent, you also have the time constant, the RC. And so the E can only be raised to a number, not something to with a unit on it. And so I have seconds in the numerator, and remember I made a point a second ago, you wouldn't think, but RC is in seconds too, and so we have seconds over seconds in that exponent, and so it is just a number. And what it's going to give you is it's going to give you this graph, which is exactly what we saw from the simulator. We said that the voltage one looks like that too, and actually it's a lot of people think it's comforting to see that the voltage is going to be the exact same pattern. 1 minus e to the negative t over RC. That gives you, this basically gives you the percentage that you're at a point in time times the maximum value. Okay. A couple real important points here. And point number one is that the first instant that the circuit's completed, you get a no resistance from the capacitor whatsoever, because putting that first bit of charge on there is no problem for the battery at all. And so at the very first instant, the flow is exactly as if it was if the capacitor wasn't there and it was just replaced by a wire. That's why when we say that we have a current, which the way to calculate the current on one of these is just the first current is the voltage of the battery divided by the resistance, as it always would be, right? V equals IR. And then as time goes by, that current starts to come down, and you can see that the way we get the current to come down is right here. So here is my maximum current, I naught, times, now this time not 1 minus e to the blah blah blah, but just e to the blah blah blah. So it's the same e term, but it's just this time it's just going to be just an e times. That when you don't do 1 minus, now the thing is going to come down as time goes up. The other thing that we'll say is as you approach that steady state, now the current is going to get less and less, because after you've let it run for 5+ time constants, the capacitor starts to show its true colors. The capacitor starts to say, hey, I actually am a break in the circuit, and I will be a break in the circuit. So at first, the capacitor has everyone fooled, and the capacitor functions just like a wire, but then after 5+ time constants, the capacitor starts to act like it really is, and it's a break in the circuit. Now, as simple as that is, the discharging circuit is even easier, because everything, I mean every graph, charge, voltage, and current all take the same shape, and it's that same shape as what you saw before. So the equation that I gave for current before, current is a current naught e to the negative t over RC. Well, that same idea works for charge, and you see down here it also works for voltage too. And so this graph over here is charge versus time, but it could also have been voltage versus time. It could have also been current versus time. And that's basic RC circuits in a nutshell. Try a few practice problems yourself. Try to explain it to someone else yourself, and show that a concept that a lot of people think is difficult really isn't that bad.